Now we're recording. All right, now I'm going to share the screen. And it's this one, right? All right, so we got f of xy is xy times 1 minus 10x minus y. We want to find all the critical points. All right. This is the one you want, right?
Yes.
Okay, so let's take a look at this one. I'm going to go to my overhead here. Um, Let me make it big. All right, well, first thing we got to do is I'm going to go ahead and distribute. And then I'm going to take partial derivatives. So make sure you do that step correctly. So partial xy with respect to x is y. Here we're going to get negative 20x y. And here we're going to get negative y squared. And then f sub y is going to be x take away 10x squared, take away 2xy. Now here you just have to roll up your sleeves and do a bunch of algebra. Turns out in the first one you can factor out a y. And in the second one you can factor out an x. You get something like that, right?
Hmm.
So what you want is you want to make sure that these partial derivatives are zero at the same time. So one answer is pretty obvious. If you set x and y to zero simultaneously, that's a critical point. So note x equals zero and y equals zero is a critical point. So that's one of them. All right. That's the easy one. All right. Now here's the thing. Let's look at this y equals zero right here. Let's come
Okay.
over here and set it into this equation over here. So hold on.
Okay. I think that's what I was missing
Yeah, so you,
is
you know that this is
switching
zero.
sides.
So we need to force this term here to be zero. So I'm going to draw a light arrow like this and follow the arrows. That's going to make 1 minus 10x, and we want to make that zero. And that's going to force x to be 1/10. So suddenly you've got another critical point, 1/10 and 0, and whatever z is. Okay. So that's another critical point. So we know that 0, 0 is a critical point. We know that 1/10 and 0 is a critical point. So far, so good?
Yes.
Now we're going to do the same thing over here. We're going to take this x, which we know is 0, we're going to plug it in there. And that's going to make 1 minus, I guess it's just 1 minus y. We're going to force that to be 0, so y is 1. So that creates a critical point of 0 and 1. Is that right? Yeah. So that's a third critical point. Now, what we need to do, we actually need to look at these lengthier factors as a system. So now, look at 1 minus 20x minus y as 0, and at the same time, 1 minus 10x minus 2y equal to 0. Do you see what I did there?
Okay. Yes.
Okay, so that's a system. And then what I'm going to do is I'm going to move some stuff around. I'm actually going to do a couple steps at the same time. I can bring these negatives to the right side and then just flop them so I have all positives. And then I have 10x plus 2y also equals 1. So I kind of did a couple algebra steps together there. And then now as far as solving a system, I don't really care how you do that. I'm going to go with the old fashioned, just multiply the top by -2. And so follow the arrows. We get negative 40x, take away 2y equals -2. And the bottom, nothing's changed. Now I can stack them and add, and I get negative 30x equals -1. So x is 1/30th. Now, if I go back and plug it in here, let's say I need to find what y is. I can plug it in any one. If I plug it in here, I get 1 over 30. So 10 over 30 is 1 over 3. So, oops, do that. 10 times 1 over 30 plus 2y equals 1. So I'm using this bottom equation to figure out what y is. So I got 1/3 plus 2y equals 1. Oops, sorry. I'm running out of space here. So I got 2y. One take away third is 2/3. And divide by 2, you get 1/3 again. So that's your fourth critical point. Looks like it's going to be 1/30th, comma 1/3. So there's your 4 critical points. Does that help?
Okay. Yeah,
Is that what you were wondering about?
Yes.
Okay. Yeah, there's just a lot of algebra on this one. It's kind of not the most fun, but that's just kind of the way you do it. Anybody else have any questions on this one? Alrighty. Same deal. We want to find min, max, or saddle. I'm going to FOIL this out because I don't like messing around with it in this fashion. So I got 16x, take away x squared y, take away 16y plus xy squared. And then I'm going to do the same thing, partial derivatives. F sub x is 16, take away 2xy. That drops out. And over here we have plus y squared. F sub y is going to be, that drops out. It's going to be negative x squared. Take away 16 plus 2x. 2xy. Okay. So far, so good. All right. Now, in this one, you get a little lucky. I'll admit. Okay, so first of all, you got to set them to 0. You got to set them to 0 because we're trying to make that happen. And I'll write it this way, just the way I wrote it. Let's see, plus 2xy. Okay. You get lucky on this one because if I add right now, you'll notice the 2xy's canceled. You'll notice the 16's canceled. And I've got y squared take away x squared equals 0. So I got a little lucky on the algebra. This is a nonlinear system. It's got a square in it. And unfortunately, when you get into nonlinear territory, there's really no one size fits all way to solve them. You just basically brute force it with the algebra and hope it works. Now, right here, I can generate some critical values. And there's a few ways to do this, but I'll do it kind of the quickie way. I think it's quick. It's just write it like this and then take square roots and you get y is equal to plus or minus x. All right, fine and dandy, right? But that's not your critical points. You still need to do some more work. So what you do is you take, let's say y equals x, and you actually plug it back in to the original functions or the original derivatives. So let's look at y equals x. And we plug back in into the partial derivatives. So I'm going to take y equals x and I'm going to plug them back up here. So I'm going to put an x there. And obviously I'm going to put x's here. So f sub x, well, again, I'm just verbalizing it. I'm replacing y with x. So it's going to be 16 minus 2x squared plus x squared. So that's 16 take away x squared. Now if I do it for f sub y, I'm replacing y with x. So that's x negative x squared. So that's actually, let me write it. That y is now an x, so it's x squared. And notice you get the same thing, actually. You get x squared take away 16. Well, they're different by a negative, but now remember, the whole point of this is to make this 0. And both of these actually give you the same solution. So when you set to 0, you get x is plus or minus 4. So y is going to be equal to plus or minus 4. So your two critical points are 4, 4, and then negative 4, negative 4. That makes it easy. Yeah, and I'll admit it, this one you get a little lucky. You know, if I, I'm not, unfortunately, nonlinear systems at this stage, you just basically use the hope method, which is you hope it works. There's actually a question that was in ed discussions that was similar to this one, and I actually was able to do the graph on Desmos, and sure enough, these turn out to be saddles. In fact, we should probably go ahead and finish this problem because I think they wanted to classify this as min, max, or saddle. So let's come back up here. We're almost, it's actually going to be pretty quick. Let's do it right here. F sub xx is, let's see, just negative 2y. F sub yy over here is just negative, it's plus 2x. F sub xy is negative 2x plus 2y. But notice that it's going to be the same thing for f sub yx. It's going to be negative 2x plus 2y. And that always happens. The mixed partials are always equal. Okay. So then I'm kind of cramming it in here, so bear with me. You do the D test where you do the partials. So f sub xx is negative 2y. F sub yy is 2x. And you have this thing. I'm going to write it this way. Quantity squared. And then what you do is you pop in, well, the x and y values, and you just see what you get. If you put in a 4 and 4, you get negative 8 times 8, which is negative 64. Actually, I think I missed this. This should be a minus sign right there. Yeah, not my bad. Sorry about that. And then if you put a 4 here, actually, those cancel. Okay. So we get negative 64, and a negative D test automatically is saddle. And you'll actually get the same thing with the negative 4. And by the way, if you go through the trouble of doing it with y equals negative x, you get the exact same steps. So there's no reason to redo it. You get the exact same things. All right. That was a fun one. Does that help, Christopher? Does that help you? Anybody else have any questions on this one? All right. So this is on practice test question 11. You have a function 2x cubed plus y to the fourth, and your domain is restricted to this thing, which is a circle of radius 6. So what we're going to do is we're going to actually perform this problem, ignoring this for now. We're just going to find partials. Let's see, I get 6x squared for f sub x. For f sub y, I get 4y cubed. Now, in these cases, when I set them to 0, I just get x and y are 0. So that's a critical point. I'll put a little circle around that. Okay. And that's going to be it for critical points from that. All right. The other critical points are going to occur on the edge here. So what I'm going to do is I'm going to actually ignore the less than. I'm just going to actually pretend it's equal because I'm looking at the edge specifically. And this is algebra. I'm already kind of dreading it. But let's see what happens. What I need to do is I need to do a substitution. I need to substitute this guy into the equation. And I think it's probably easiest to solve for y squared. You get y squared is equal to 36 minus x squared. And so then kind of follow the arrows. That y to the fourth is actually y squared squared. So I'm going to write this all in terms of x. It's going to be 2x cubed plus 36 minus x squared quantity squared. Does everybody catch that little subtlety? Yeah, let me know if you want that explained. So basically, I just treated y to the fourth as y squared squared. So this is y squared, and I'm just squaring it again. All right. As far as finding critical points on this now. I think I'm going to go ahead and distribute that out. So 36 squared, I should know that, but I think it's 216. 1296, my bad. Take away 72x squared plus x to the fourth. So that's the function in terms of x along the boundary. If I take the derivative, now we're just doing traditional calc 1. I get 6x squared. The constant drops out. I get negative 144x, and then I get plus 4x cubed. And I got to set that to 0. I can I guess let me divide out by 2. I'm going to factor out an x. I'm going to divide it out by 2. So that's 3x. Take away 72 plus 2x squared. Okay. And I'm going to pause here because I'm getting into some heavy algebra. Is everybody okay with these steps? Let me know if you have any questions on that. You're so far so good? Okay. This is going to work. It's probably not going to be pretty. Right there, that's an answer right there. X is 0. Interestingly enough, now that we're on the boundary, what you do is you take that X and you go back up to the boundary up here. So in fact, I'm going to do it over here. So you plug it back into the boundary. And that gives you two values for y, plus or minus 6, because when you take the square root, you generate two y values. So you actually have two critical points that come from that. All right, that's cool. And then this guy right here is quadratic. I'm not going to try to factor that. I'm just going to use the quadratic formula. Let's see. Negative. So A is -2. Negative. Well, B actually is. I'm going to just write it the usual way. So it's -3 plus or minus B squared, which is 9, take away 4 times A times C all over 2A, which is 4. Let's see what number we get out of that. 72 times 8. The negatives cancel. And then we're going to add 9 to that. We get 580, square root 585 over 4. Everybody catch all that? All right. Well, guess what? Those are a couple more critical points. I think what I'm going to do, because it gets a little messy here, I'm actually going to generate a couple of decimal equivalents. So -3 plus rad 585 quantity divided by 4 is 5.297. And the other one that I get is when I subtract and then divide by 4, and I get -6.796. Now, one of those can get kicked out right now because this is going to be outside the circle. Okay, the circle only has a radius of 6, so x is between -6 and 6, so that guy's gone. So that's another critical point, right? Well, a part of a critical point. What you need to do is you just need to find what the y value is. I just plug it in back up here. And actually, because we're going to stick the square root, we're going to get two y values. But let's take the 5.297, plug it in up there. Let's do that. So 36 take away 5.297 quantity squared, and then take the square root of that, and you get two values. You get 2.818 and -2.818. All right, so you've got 5 critical points. And again, I'll pause and let you absorb that algebra for a moment. I can go over any step that you're wondering about. Anybody have any questions on that? Hanging with me there? Okay. Actually, the rest of the problem is not too bad. What you do, and I'll just verbalize it. I'll just write it down, but I'm not gonna actually write the numbers. You just find the z values for each of these points, the largest is your absolute max. The smallest is the absolute min. And the rest, you just ignore. You don't need to use the d-test or anything like that. This one's just pure comparison. Okay. Okay. Yeah, a lot of people forget the plus and minus. That's a common mistake. Very common. So anytime you take a square root, you got to put in the plus minus. Anybody else have any questions on this one? All right. All right, so this is number 9 on the practice test. So which part were you wondering about? Were you wondering about the actual evaluation or?
Yeah, about the evaluation.
Okay, let me copy it down. We got,
I think I'm just getting confused on the which to evaluate first.
right. Me. Actually, oh, there should not be a radical on that top one. All right. So first of all, let me make sure that everybody's comfortable with the notation here. This is a dx dy integral. It means that as you travel to the right on the graph, so you could just kind of envision an arrow going to the right. Can you guys see my cursor when I do that? My little finger there? Does that show up? I
Yeah,
hope.
it does.
Okay. So as you draw an arrow to the right, where does it enter the graph first and where does it exit? And here, this is actually the arc of the parabola um, x equals y squared, or equivalently, what? I'm sorry, I got that backwards. Y equals x squared. Wait, that's wrong. Hold on, this is weird.
Yeah, I got really bamboozled on that one. It took me a while to finally accept that the graph was B. And then when I solved, it was a negative number. So they just swap it on you for fun.
Yeah, no, this is weird. Yeah, the way it's written, this is not correct. I'm gonna actually, you know what? I'm gonna take a screen capture of this. I'm gonna send it in. It's not. Give me a second here. I'm doing this for my own. And again, this was practice test, student number 9. Okay, I'm gonna. All right. You know what? Ignore the graphs for a moment. I'm just gonna. The graphs are misleading. They're actually messed up. So I apologize for that, but that can be fixed. All right. So it's actually x cubed y squared, make those more obvious. All right. So here's what I'm going to do is let's take a few moments here and discuss just what have we got going on here. I find it helpful on these bounds to write them as little expressions. So x equals rad y, x equals y. And x equals rad y is actually the same as this curve right here. This is x equals rad y. It's the same as y equals x squared, because if you square both sides, you get that. And then x equals y is the same as the line, well, the 45-degree line. So okay, it was the right one. It was just a little funny. But you know what the problem is that as a dx integral, you actually are going this way, and you should be entering at y and exiting here. So that's the problem. This is actually written backwards. So that's something that needs to be fixed. It's not, I'm going to say this, it's not incorrect, it's just poor form. Okay. As a dx dy integral, let me show you that you would draw an arrow in the x direction, and where it enters is your lower bound, where it exits is your upper bound. It enters at x equals y, and it exits at x equals square root y. And that would indicate that your bounds are like this. So that is
Okay.
I guess you could say it's a syntax issue. Your Y bounds are good to go. There's no changes there. This is actually a 0.11. So you're between 0, 0 and 1, 1. All right, so I can get that fixed. That's not going to be that hard to do. I'll have to send it up to the people who are in charge, but probably won't be in time for tonight, you know. All right, well, I'm sorry about that because this is actually not quite 100% kosher. All right, so your question then is how do you actually solve this?
Yeah.
Okay, so it's a dx integral. I'm just going to work out it. I'm just going to work it out as I'm going to basically ignore the y squared for a moment. I'm just going to work this out. This is going to be raised to the 4 and divide by 4. So 150 over 4 is the same as 75 over 2. And that's going to be x to the 4th. And I pop in the rad y and the y. And let's see, when I do that, I get 75 over 2. Now, rad y to the 4th is the same as y squared. And when I pop in the y, I just get y to the 4th. And then I'm going to take that, I'll just factor out the 75 over 2. And then I'm going to integrate that with respect to y. Now, this y squared has been sitting out in front. So watch out. You still have this y squared here hanging out. Now you've got that. And then let's finish it off. It's going to be integral y to the 4th, take away y to the 6th, dy. 75 over 2, that's going to be 1/5 y5, take away 1/7 y to the 7th. But the nice thing is we pop in the 0 and 1 bounds, it's pretty. You can get 1/5 take away 1/7, and then the zeros just drop out. And what do you get there? You get 35, 2 over 35, so 75 over 2, 2 over 35. These cancel. 75 over 35 divided by 5, you get 7 and 15. So you should get 15 over 7, I hope. Okay. Did that help?
Yeah, definitely. I just met with a tutor the other day to go over them, and he made it a lot more complicated. So I just needed an example that was a little clearer. So thank you.
Okay. Well, the way the problem is written, it actually got me kind of confused because neither of the two graphs were quite matching up with this. This is actually backwards.
So I actually also got kind of stuck on that graph thing. But like I said, I did get a negative. So is that just like swapping the bounds, just not really something that you do for this kind of thing, or like
This is, if you evaluate it the way it's written, you will get a negative answer. The only change will happen right here. You'll actually have 1/7 minus 1/5.
yeah, so like technically it does work out as a negative. I just mean like um you just don't typically see it going right to left. Like that's not something that's usually done.
No, whenever you
No,
set it up
okay.
as a dx dy, you're always going left to right in the traditional orientation. So my concern with this problem is that as it's written, yeah, you will get negative of this value here. So this is the answer to this one's actually negative 15 over 7. But it normally we would not do this. This is basically just poor form. It's not incorrect, it's just clumsy. So I'm gonna,
Okay, I had assumed it was like trying to trip us up or something, but
well, that's what it's
good to
doing.
know that that's just okay.
I don't think it's a fair question. So, I mean, if you didn't know any better and you just kind of tackled it and you just trusted the math, you'd get negative 15 over 7. That would be your answer. You'd be good to go. The problem with it is that they wanted you to match it up with one of these graphs. And that's actually neither of the two graphs were actually correct, according to the way the integral is written. So I shall talk with them. No big deal. All righty. Any other questions on this one? So this is 12(3), number 15. Find the volume of the wedge-shaped region, figure 1, contained in the cylinder, x squared plus y squared equals 9, so that's this guy, and bounded above by the plane z equals x, and below by the xy plane. Okay. I'm not going to even look at the solution yet. I'm just going to copy it, copy the picture. You got a plane that's kind of slicing through at an angle. You get kind of a wedge shaped thing. Draw. It's actually going to exist. It's so first of all, can you picture the shape? It's basically a well, they say a wedge, but that's kind of vague. I'll draw it.
Yeah, I was less confused about the question and more confused about, as I said, it's in like the homework assignment for double integrals and polar coordinates, but the get help is
Yeah,
done in uh, XY.
right.
I guess not for you.
No, this is the solution, but the get
Oh,
help is
okay.
right here, and I'm gonna. This is what the get help says. Um, what the heck? Yeah, this is nonsense. Yeah. All right. Ugh. Just a second here. I'll tell you what. Yeah, ignore this get help. The whole point of this is to do it in polar. Okay. So clearly, I mean, it works. First of all, I throw an X in here right there without explanation. So I'm gonna just ignore it. And I'm just gonna do it the way I would do it if we were in class. So I've copied the question down. Um, and let me go ahead and stop the share here. Okay, so the trick is to kind of get the base. What does the region of integration look like? And it's going to be a half circle. Now z equals x. Let's see if that's going to be coming down from the first and fourth quadrants. All right, so you know what? I'm going to draw it this way. It's actually going to look something like this. So here's x, here's y, and then the z is coming out like this. And z equals x would actually be a plane kind of coming down. So it'd be over the first and the fourth quadrants. Okay. So the volume of it is just simply double integral dA. That's your standard way of writing volume. Okay. The integrand is a 1 until further adjustment. All right. So first order of business is we decide do we want to do polar because it makes sense. It's a shape here. So the integral is going to become r dr d theta. Okay. The now here you kind of have to ignore this. I'm going to draw it again. I'm going to try to draw it with some perspective. It's kind of hard to draw wedges. It's going to be kind of like this. So you have z equals x here, and then on the bottom you have z equals 0, which is the xy plane. And so when I do my okay, that's where the x came from. So I'm going to throw an x in here temporarily because that's just the top. That's basically the area and the volume under the surface. We're going to replace that x here in 2 seconds. So first of all, what would be your r bounds? So just looking at your picture here, the r and the theta just govern the region of integration. So if you draw an arrow from the origin outward, it's already in the region. So r is 0 and it exits the circle at 3. So 0 to 3. Your theta bounds are going to be what sweeps out the region, always counterclockwise. So it's going to be negative pi halves to pi halves. Okay. I left some room there for that x. Okay, the x actually comes from, again, the volume below this surface. Okay, now it's above the surface x0, so we don't need to worry about that. X, we can't use x, we have to replace it. So normally you replace x with r cos theta. Okay. And again, I'll pause and let you, are you okay with that?
Yep.
Okay. Now, the way the get help has you do it, they're doing it all in Cartesian, which I think is ridiculous. The whole point of this is to do it in polar. Let's clean this up a little bit. The r's make r squared. We have cos theta. We have dr, d theta. If I do the dr integral, ignore the cos theta, just let it ride for a moment. It's 1/3 r cubed from 3 to 0. That's 27 over 3, which is 9. All right. So now I've got 9, which I can factor out to the front. Integral from negative pi halves cos theta, d theta. That's going to be 9 sine theta. And sine of pi halves minus sine of negative pi halves. Well, sine of pi halves is, everybody all together, it's 1. Sine of negative pi halves is actually a -1, but then this negative makes it a positive 1. You actually have 1 plus 1 is 2, so 18. So 9 times 2 is 18. Does that help? Does that make sense?
Yep.
Okay. Anybody else have any questions on this one? Let's see. Okay. Well, the exam is open now until no, it's actually open until midnight tomorrow. So 30 hours. You've got until now and until 11:59 p.m. There you go. And I'll post this video on YouTube if you want to review it. It'll give me about an hour. It takes about that long to get it figured out. All right. Any last questions, concerns? Okay. Well, Desmos, yeah, you'll be given the same ones that you were given on the first test. I just make all 4 of them available. So you get the scientific, the graphing, this 3D, and the matrix. I don't think you'll need the matrix, but what the hey, I give it to you. All right, people. Well, I'm going to go ahead and power down here. And thank you again. Good luck on the test. And any further questions, especially from the practice, put them on to ed discussions I'll be monitoring throughout tonight and tomorrow. And well, I appreciate it. So I'm going to go ahead and log off. Good luck to everybody. Did you see that happen? Whoa, that's kind of cool. All right. All right. Bye-bye, everybody.